Okay. And then you have plus omega naught L4 over 24, right? And you have C4. So now we can determine our C4. So C4 will be equal to 1 over 120 minus 1 over 24 will be equal to minus omega naught L4 over 30. Okay. Now, when you're doing this, it's always the case that you always have L to the highest polynomial that you can observe. Now, if your C4, you get minus, for example, okay, you get minus omega naught L4 over 10 plus by omega naught L cubed over 22, there's something wrong. It has to be only, it's either L4 or L cubed, okay? It cannot have L4 and L cubed. Are we clear? When you, so like for this case, you have L to power 4. You cannot have L4 and L cubed as your defined constant. Okay. So when that's the case, finally, y as a function of x or ei, y as a function of x, you have minus omega naught x5 over 120L plus by omega naught L cube x over 24 and then minus omega naught L4 over 30. Okay. So what you have now is y as a function of x. So this is equal to 1 over ei. Okay, 1 over ei. And then minus omega naught x5 over 120L plus by omega naught L cube x over 24 minus by omega naught L4 over 30. Okay, so this is the equation for or the deflection equation as a function x. Okay. Okay. So now I believe your I believe you could see. So the most important thing from here, okay, just to quickly summarize elastic curve. Okay, is the most important thing are the what? Boundary condition. And what we have done, okay, is we came from dv over dx is equal to minus omega as a function of x, right? Then we do integrate, right? So when we integrate, we have v as a function of x, we have minus omega x dx, okay, or omega, yeah, dx. Then this will be equal to dm by dx. Then we do integrate the second time, right? So we have m as a function of x. We integrate twice minus omega as a function of x. we integrate twice. And then from here, we let this equal to EI d squared y over what? Dx squared. By this, over here, when we move to this stage, we apply the elastic curve equation. And then from here, we integrate again EI theta or EI dy by dx. And this is also equal to our EI theta. And that is the third integration. Which is 1, 2, 3 minus omega as a function of x, 1, 2, 3. And then finally, we integrate the fourth time. We have what? EIY, and then this is integrated 1, 2, 3, 4 minus omega as a function of x, 1, 2, 3, 4. Okay. So what I want you to realize is this: V M theta y. Okay, so that is why when I make you set up your boundary condition, okay, it's for that reason I make you all do what? V M theta y. Are we clear? So you'll not be confused. Okay, you just remember VM theta y. So with the equation of distributed load, you integrate y, you get a shear force, you integrate a second time, you get bending moment. Then you apply your elastic curve theory, then you integrate to get your slope, and you integrate again, get your deflection. Okay. Now we go back to buckling. Okay. And I want you to look at this now. Okay. I want you to look at this. I want you to start to get familiar with this. Okay. I'm going to what I'm going to do is get you to be comfortable with boundary condition. Okay, so we have one like this. We have another one. Okay. And I want you to get familiar with this. What does it actually means? Okay. And how to identify which condition, more important. Okay, so now, oh, I forgot which one I copy now. Both end fixed, both end pin, and I have one end. Okay, now we have all this. Okay, let me, yeah, okay. So as I said, you can get all these figures on Avenue to Learn. Okay, so let's look at the first one. Okay, okay, let's look at the. So what do we observe? Okay, okay. When you see all this diagram, the best advice is to draw the centroid before deformation occur. Okay, so I'm going to draw the centroid. Bear with me. Okay. Okay. Right. So the first one, they call one fixed end and one free end. So we see the word fixed and we see the word free. Okay. And I just constructed our green line. So at point B, right, is as good as moment is not equal to 0. Yes or no? Another thing to look at is if you look at the deformation pattern, right? The slope is 0, then it curve. Can you see that? That's what I'm. So down here, theta slope is also equal to what? 0. Okay. So when slope is equal to 0, moment is not equal to 0 in this case. Okay. So when moment is equal to 0, and you can see, so this is the fixed end. Yeah, I want you to be able to see this. And then it's very obvious. The other side is free. Right? Point A is free. So originally, point A is somewhere around here originally. And because it's free, point A can go towards the right or it can go towards the left. Does not matter. Okay. So what we realize when it's P, when it's free, the P is not aligned with the centroid during buckling. And you see that? Okay. So that's where you classify as one end is fixed, the other end is free. Okay. We okay so far? So we have condition. So free means the force can go away from the centroid. Okay, that's what we call. Now, okay, now let's look at the next one. Okay, again, I draw a green line. I'll draw a green line. I'll draw a straight line. Okay, and then I'll shape it so you guys know that it's aligned. And you see that? Okay, it's aligned. So this is called pin and pin. Okay. So when it's pin and pin, what does it? So at point A, right? At point A, M is equal to 0. At point B, M is equal to 0. Why is that? Because if I were to remove the support at A, right, the structure will just rotate about point B. If I remove the support at B, assuming there's no gravity, okay, A will also tend to rotate. So moment is equal. So when that's the case, we also realize that theta, the slope, is not equal to 0 anymore. Okay, theta is no more equal to 0. So when that's the case, if you look at the deformation pattern, so I'm going to sketch the deformation pattern, right? So when you see that, right, and if I were to draw a line, right, you draw a line, and this is our theta now. And then if I were to draw another line, okay, line, okay, come on. Right? This is now our what? Our theta now. Okay. So this is what we call pin. Okay. Pin at both ends. And you realize when it's pin at both ends, the P during deformation, the P is still aligned with the centroid. Oh, sorry, P is still aligned